In the previous class, we studied various types of transforms: Fourier series, Fourier transform, Laplace transform, Z transform. And we started our discussion with understanding Hilbert transform. So with the basics of Fourier transform, we can write any time limited signal g of t can be written in frequency domain by using Fourier transform equation, and the Fourier transform of rectangular pulse is as shown. It is sinc function. From the basics of Fourier transform, let us try to understand Hilbert transform. We are now going to analyze Hilbert transform, that is nothing but introducing phase shift of plus or minus 90 degree for each and every component of the input signal. So here we are going to analyze Hilbert transform in time domain as well as frequency domain analysis, and then we are going to understand some properties of Hilbert transform. So for a LTI system, that is linear time invariant system, which is having input x of t, system response h of t, which is given by 1 by pi t, with output y of t. Y of t is nothing but Hilbert transform of x of t. Here we have written x cap of t. So in time domain, we can write expression for y of t, that is given by y of t is equal to convolution of x of t and h of t. So h of t is nothing but 1 by pi t. Substitute and express this equation in the form of convolution integral, that is given by integral minus infinity to infinity x of tau into 1 by pi into t minus tau d tau. So simplifying, we are going to get Hilbert transform of x of t is given by x cap of t, that is equal to 1 by pi integral minus infinity to infinity x of tau by t minus tau into d tau. In the same way, here time domain signal can be represented by frequency domain by using Fourier transform, and inverse transform is also exist. Therefore, if I have Hilbert transformed signal as shown here, x cap of tau, I can obtain x of t, that is given by this equation. X of t is equal to minus 1 by pi integral minus infinity to infinity x cap of tau by t minus tau into d tau. Both equation 1 and 2, they are considered and called Hilbert transform pairs. This is nothing but the time domain analysis. This is nothing but the time domain analysis. Now we are going to consider frequency domain analysis of Hilbert transform. From this equation, here, it is clear that time domain signal can be represented in frequency domain using Fourier transform. Therefore, Therefore, x of t in frequency domain is represented by x of f, and Fourier transform of this h of t LTI system is having h of f, and y of t is represented in frequency domain y of f. That means Fourier transform of x of t, h of t and y of t is represented in this block diagram. So in frequency domain, output for y of f is given by Hilbert transform in frequency domain, that is given by multiplication of these two sequence, that is x of f into x of f, h of f and x of f. But here the frequency domain, but the Fourier transform of h of t is given by minus j signum function. That means this is the Fourier transform of h of t in frequency domain. So on substituting this in the equation, we are going to get the Hilbert transform in frequency domain is given by minus j signum function into x of f. How signum function is defined? Signum function is given by positive, for positive frequency, that is f greater than 0, it is having amplitude plus 1. For frequency is equal to 0, it is having 0, and for negative frequency it is having minus 1. So this signum function equation is represented in the form of picture or diagram like this. So positive frequency, negative frequency, plus 1 amplitude and minus 1 amplitude. Now I am going to multiply this signum function with x of f. So if I consider the amplitude spectrum and the phase spectrum of this signum function, we are going to write this waveform. Since magnitude of signum function we have considered here, it is always positive here, because minus j signum function means if you square it, any negative value becomes positive. For all frequencies it is having magnitude 1. If we consider the phase, we are going to see here, for positive frequency signum function is having positive value, but if we multiply that with minus sign, so we are going to see the negative value here. For negative frequency it is minus 1. If we multiply that with minus into minus is plus, so we are going to get plus 90 degree phase shift. This indicates that the Hilbert transform introduces negative phase shift for positive frequency and positive phase shift for negative frequency by 90 degree. So what are the properties of Hilbert transform? There are few properties which is mentioned here. First one is x of t and x cap of t have same energy spectrum, that is original signal and Hilbert transformed signal have same energy spectrum. If we take Hilbert transform twice on x of t, which results in minus x of t, that means x cap of t is equal to minus x of t. X of t and Hilbert transform of x of t have same autocorrelation function. So positive frequencies have phase shift minus pi by 2 and negative frequencies have positive phase shift. These are some of the properties of Hilbert transform, and we are going to prove some of the properties in the next class. So in today's class we learned analysis of Hilbert transform in time domain and frequency domain, as well as the properties of Hilbert transform.